Hello viewers and welcome back to my channel. Continuing the eigenvalue, eigenvector and diagonalization series, we will be now heading on to the orthogonal diagonalization of matrices. And to get onto that topic, we need to understand what orthogonal matrices are. So I have added this video so that we bridge that gap, which might be a missing link in learning orthogonal diagonalization of a matrix. So let us get started with the definition of orthogonal matrix. A matrix A of order n by n is said to be orthogonal if A times A transpose is equal to the identity matrix of order n, and so is the product A transpose with A. And if any matrix satisfies this condition, then we say that the matrix is going to be an orthogonal matrix. Now we are very much aware that A times A inverse is always equal to identity whenever the inverses exist, and so does A inverse time A. And if we compare this with our earlier expression in the definition of orthogonal matrices, then we can understand that a matrix A is orthogonal if A inverse is going to be the transpose of the matrix A itself. Thus you can see that finding inverses of an orthogonal matrix is the easiest one to do.
You just got to take the transpose of the matrix provided you know that it is orthogonal.
Now let us see a couple of examples. We will first start with a 2 by 2 matrix A. So let's take the matrix A as 1 over root 2, 1 over root 2, negative 1 over root 2 and 1 over root 2. And if we talk about its transpose, then the transpose is going to be the first row becomes the first column. So the first column will be 1 over root 2 repeated values, and then we will have negative 1 over root 2 and 1 over root 2 in the second column. Now let us take the product of A with its transpose. So this is going to be 1 over root 2, 1 over root 2, negative 1 over root 2 and 1 over root 2 times 1 over root 2, negative 1 over root 2, 1 over root 2 and 1 over root 2. So taking the product of first row with the first column, we get 1 by root 2 times 1 by root 2 will be half, and then we will get another half. And likewise, if we take the product of first row with the second column, so then it is going to be again negative half and plus half. Taking the product of the second row with the first column gives us negative half plus half. And likewise, if we take the product of the second row with the second column, we are going to get half and half. And thus you can see that it reduces to 1, 0, 0 and 1, which is the identity matrix of order 2 by 2. Thus one can conclude that the given matrix A is orthogonal. And using this, you can say the property, finding the inverse of the given matrix A is as easy as saying that A inverse is going to be A transpose, and that is going to be 1 over root 2, negative 1 over root 2, 1 over root 2 and 1 over root 2. Thus identifying if a given matrix is orthogonal is really helpful in order to find out its inverse. Now let us also quickly state a matrix B which is going to be orthogonal, and it is going to be a 3 by 3 matrix. So consider the matrix 3 over 7, 2 over 7, 6 over 7, followed by negative 6 over 7, 3 over 7, 2 over 7, and lastly we have 2 over 7, 6 over 7 and negative 3 over 7. So next what you can do is you can find out B transpose and take the product of B with B transpose and check if it is coming out as the identity matrix, and if it does, then you can conclude that B is going to be orthogonal. And I also want you to find out what is B inverse in that case. So this is a pretty short exercise which will help you know that whether you have understood the idea of orthogonal matrix or no. Now next we are going to talk about some standard matrices which are orthogonal in nature. So if you have heard about the rotation matrix, to understand the rotation matrix, let me give you a brief idea what it is going to be. So suppose say we are in the xy plane and I have a vector over here, call it as xy. Now if I join this with the origin, then this is the radial vector, corresponding radial vector to the assigned one. And suppose I wish to rotate this particular vector with a specified angle, let's say theta. So if I rotate this vector by theta, then this would be the new position of your image, x prime, y prime. So since it's a linear transformation, we have a corresponding matrix for it, and the matrix which we get is known as the rotation matrix, and it is given by, let's say, A is equal to cos of theta, negative sine of theta, sine of theta, and cos of theta. So it's not again very difficult to check whether this is orthogonal. So if I evaluate A transpose, then it is going to be cos theta, negative sine theta, and cos theta. Now let's take the product of A with its transpose. So that is going to be cos theta, negative sine theta, cos theta times cos theta, sine theta, negative sine theta times cos theta. So the first entry is going to be the product of the first row with the first column. So that's cos square theta plus sine square theta. And then for the next one, we will have sine theta, cos theta minus sine theta, cos theta. For the second row, first entry, we will have sine theta, cos theta minus sine theta, cos theta. And the A22 entry is going to be sine square theta plus cos square theta. And using the trigonometric identities, this is 1, this is 0, 0, and this is 1. So thus it can be seen that A times A transpose is the identity matrix of order 2, and therefore we can say that A is an orthogonal matrix. So here is another quick fact, that the reflection matrix given by negative 1, 0, 0, 1, 1, 0, 0, negative 1, these are reflection matrices. This is along the y-axis and this is along the x-axis. These two matrices are also orthogonal. I will be quickly stating some results, you can say in a form theorems, which are in a way really helpful to reduce lot of work when you'll be solving problems from IIT JAM, CSIR, NET, GATE or SET examinations. So the results are like this. So if a matrix A is orthogonal, this implies and is implied by that its inverse A inverse is orthogonal. So you can quickly have a proof of this, it's not going to be really difficult. Then if A and B are orthogonal matrices of same order, this implies that the product AB is also going to be orthogonal. And lastly, we are going to state that the determinant of an orthogonal matrix is either plus or minus 1. So that's all in this video. On the basis of the ideas and concepts that you have understood in this video, we'll be next moving on to the orthogonal diagonalization of symmetric matrices. So catch me up in the next video. Thank you so much for watching till here and happy learning.